Welcome to In Silico Trials Real Impact, the In Silico UK podcast that's revolutionizing the way we think about medical innovation. I'm Professor Alejandro Frangi from the University of Manchester, and I'll be your guide through this fascinating world of in silico technologies. In each episode, we'll dive into cutting-edge research and groundbreaking news that are shaping the future of medical product development and regulation. From computational modeling to simulated clinical trials, we are exploring how digital approaches are transforming healthcare, making it safer, more efficient, more equitable, and incredibly precise. So, whether you're a researcher, regulator, a member of the public, or a patient representative, or simply curious about the future of medicine, tune in as we unravel the complex world of in silico methods and their real-world impact. Get ready to discover how computer-simulated trials are leading to very real breakthroughs in patient care. In Silico Trials, Real Impact, where algorithms and data are saving lives. Let's begin.
Welcome back, everyone. You know we love when you send us stuff to dig into, and this time you've really outdone yourselves. RCTs, randomized controlled trials. Everywhere you look, people are talking about them like they hold the key to the universe. But you've sent over this whole stack of articles and studies that really get into, well, whether they're cracked up to be.
Yeah, they really are seen as this sort of gold standard, like the ultimate way to figure out what causes what. But you're right, there's this whole other side to the story about their limitations, how we interpret the results, even some pretty basic misunderstandings about what they can and can't tell us.
And that's what we're diving into today, right? This deep dive is all about looking beyond the hype, unpacking these common and sometimes pretty misleading ideas about RCTs. We're going to be relying heavily on this Deaton and Cartwright paper, Understanding and Misunderstanding Randomized Controlled Trials. They really bring up some fascinating challenges.
Absolutely. They make it very clear that they're not anti-RCT. It's more about being, I guess you could say, anti-magical thinking. This idea that just because it's an RCT, the conclusions are automatically rock solid. We'll be looking at why that's not always true, why applying findings from one RCT to a whole different situation can be really problematic, and why RCTs are really just one tool in the toolbox, so to speak.
It's kind of like thinking you can solve any problem with just a hammer, right? You need screwdrivers, wrenches, the whole set. So let's start with something I think everyone has heard a million times, but maybe with a little twist. RCTs, especially in medicine and social sciences, they're seen as the super reliable way to get at cause and effect. What is it about them that makes people think they're the ultimate truth machine?
Well, the basic idea is pretty simple, right? You take your group of participants and randomly assign them to either get the treatment or not. That's the control group. And that random assignment is supposed to make the two groups basically identical on average, except for whether they got the treatment. So any differences you see in their outcomes, well, that's supposed to be because of the treatment. And one reason people see them as so powerful is that you don't need to go in with a ton of assumptions about why the treatment might work. You just see if it works in the trial.
And that's appealing, right?
Yeah.
Less room for bias to creep in.
Exactly. You're not relying on experts' opinions or just looking at what happens naturally. Plus, there's been this push for things like pre-registering trials and sticking to those plans for analysis. All of that is meant to make sure researchers aren't tilting the scales, even subconsciously.
That makes them seem more objective, like a pure test. But then you have people like Frieden, former head of the CDC, saying, hold on a minute, there are definitely cases where RCTs aren't the ideal tool, or even where they have some pretty big downsides. What are some of those situations where another approach might actually be better?
Frieden brings up some really important points, like think about rare diseases or things that take decades to develop. Trying to do a huge RCT for those is incredibly difficult and takes forever. Or in a situation where you need answers fast, like an outbreak of some infectious disease, observational studies can actually be much more useful because they can quickly identify risk factors and tell you how it's spreading. And he also reminds us that RCTs, by their very nature, are kind of artificial. They don't always capture all the messy real-world complexities where tons of things are interacting all the time.
It's like trying to study how birds fly by putting them in a wind tunnel. Gives you some info, but it's not the whole story.
Yeah, exactly.
And that's basically Deaton and Cartwright's whole point, right? There's no magic bullet method. The best approach depends entirely on what you're actually trying to find out and what you already know going in.
Exactly. They're not saying RCTs are useless, but they really challenge this, almost worshipful attitude toward them. They say that when we don't understand the basics of a situation very well, no single method is going to give you completely reliable conclusions. Not even an RCT. RCTs are at their best when they're part of a bigger effort. You've got your theories, your findings from other research, your existing knowledge, and then the RCT adds a piece to that puzzle.
Okay, so let's get into what an RCT can tell us, starting with the trial itself. We always hear about the average treatment effect, the ATE. Within that particular group of people in the trial, what can we say about what's going on in the treatment group versus the control group?
So within that trial, a well-run RCT lets you estimate how outcomes are spread out, both for those who got the treatment and those who didn't. And the ATE, that average treatment effect, is just a difference in the average outcome between those two groups. It's specific to those people.
But, and the paper makes a big deal out of this, the people in the trial aren't always a perfect representation of everyone we're interested in, right? They're often volunteers, and they might have some specific characteristics that make them different from the larger group we want to apply the findings to.
Right, and that's hugely important when we think about what we can say beyond the trial itself.
Yeah.
The ADE we get, it applies to those specific people in the trial. So if they are, say, healthier or more motivated than the general population, the ADE from the trial might not be what you'd see in that broader group.
So it's very context specific.
Yeah.
The paper uses this schematic model, equation 1, to show how treatment effects and other stuff influence outcomes. What's the main point about individual treatment effects that we get from that model?
Equation 1 basically shows you, in the mathematical way, that someone's outcome isn't only determined by whether or not they got the treatment. There are all sorts of other factors at play. Some we can measure, some we can't. And the key thing there is this term, PEEP, which represents the individual treatment effect. Like, how much did the treatment affect that specific person?
So not everyone's going to respond the same way.
Right, exactly. Some people might benefit a lot, some a little, some not at all. Some might even have a negative reaction.
Which takes us to the whole counterfactual idea, the Rubin causal model, where we realize it's impossible to know what would have happened if someone both received and didn't receive the treatment at the same time. We only get to see one of those possibilities.
Exactly. You only see one version of reality for each person. The individual treatment effect, it's the difference between these two things we can't observe. And this is where what Deaton and Cartwright call the remarkable theorem comes in.
Okay, what's so remarkable about it?
It says that even though we can't see those individual effects directly, if you have a well-conducted RCT, just the simple difference in the average outcomes between the treatment and control groups is an unbiased estimate of the average of those individual effects within the trial.
So we can get a handle on that average effect even though we can't see the individual pieces that make it up.
Right. As long as we're willing to assume that the other stuff influencing outcomes is on average the same in both groups. But here's the catch it only applies to the average, not to things like the median or how much variation there is in the effects.
So if you're interested in how the treatment affects the whole spread of outcomes, like does it reduce the number of people with really bad outcomes? Does it help a certain subgroup more than others? Just looking at the average might not be enough.
Right. You need to make more assumptions, stronger ones, or use different statistical techniques.
Okay, let's move on to randomization. This is like the core of RCTs. But what does it actually do in a single trial? And what are some things people often get wrong about what it guarantees?
So randomization is all about making sure that whether someone gets the treatment or not has nothing to do with any other factor that could affect the outcome. By randomly assigning people, you're trying to create these two groups that are, on average, balanced, not just on things we can see, like age or income, but also things we can't, like hidden health conditions or their motivation. It's about getting rid of any correlation between treatment assignment and all these other potential causes.
But this seems important. That balance is what you'd expect over many trials, not necessarily what you get in a single trial, right?
Absolutely. You can still get imbalances just by chance. Deaton and Cartwright call this random confounding or realized confounding. Just because you randomize doesn't mean every single trial is going to have perfectly balanced groups. You might get one group that just happens to have more people with a characteristic that affects the outcome, and that can mess things up.
So the observed difference might not be entirely because of the treatment. It could be partly due to this random imbalance. And just thinking historically, wasn't Fisher the guy who really pushed for using randomization in those early agricultural experiments? Aware of this?
Yeah, he was. His point wasn't that randomization means perfect balance every time. His big insight was that it gives you a solid way to calculate how big the error from those random imbalances might be. That's where the standard error comes from.
So it's more about understanding the uncertainty than guaranteeing perfect precision in every single trial.
Exactly.
Okay, there's this quote in the paper from like a big development organization, the Inter-American Development Bank and World Bank, that seems to really misunderstand this point about randomization. What did they say that was so problematic?
They basically said that because they used an RCT, they could be absolutely sure the result was the real deal because they had eliminated all the other factors that could explain the difference, observed and unobserved. And that's just not true.
It's confusing what you'd expect on average with what you actually get in one trial.
Right. If everything was truly eliminated in each trial, then yeah, the result would be the exact treatment effect. But that's not what randomization does.
It's not a magic wand. And there's another quote, this time from a psychiatrist, about genetic variations automatically being balanced. What's wrong with that line of thinking?
That one's tricky because with enough people, yeah, randomization is more likely to balance things out, even stuff we can't measure like genetics. But it's still a random process. You can't be 100% certain.
There's always a chance of some imbalance.
Right. So to just say, well, it's an RCT, so the treatment must be the cause, without thinking about the possibility of those imbalances is risky.
Okay, so this takes us to something researchers often do after they've randomized balance testing. They look to see if the treatment and control groups look similar on different characteristics at the start of the trial. But the paper suggests this might not be as useful as we think. Why is that?
Well, technically, what you're doing is testing a null hypothesis that you already assume is true, that the randomization worked. If you find a significant difference, yeah, it could mean something's wrong with how you randomized, but it could also just be chance.
So it's more about checking the process than proving perfect balance?
Right. A non-significant result doesn't tell you much about how precise your 8E estimate is. You could have a test that's just not powerful enough to pick up a real imbalance.
And what about adjusting for those imbalances statistically, like using regression analysis?
It can be helpful sometimes, especially if you're trying to get a more precise estimate. But, Friedman's research shows that it can actually introduce bias in certain cases.
Yeah.
So it's not a guaranteed fix, it's a trade-off. You might get a more precise estimate, but it might be more biased.
This is getting complex. Now, the paper brings up something really interesting philosophically. The Bayesian view on randomization. Bayesians don't necessarily think randomization is always the best way to assign treatments, do they?
Yeah, and it all comes down to this idea of prior beliefs. Like, what do you already think is true about the world? Bayesians, and we're talking about people like Savage and folks who followed him, they say that sometimes the most informative way to learn isn't to just randomly assign treatments.
Because if you have strong beliefs about how things work, you might be able to design a study that gives you more information than just randomly doing things.
Right. They use this example of a school administrator who's convinced that family background is the biggest driver of student success, much more so than school quality. A Bayesian would say, maybe you'd learn more by deliberately putting disadvantaged students in the good schools and privileged kids in the not-so-good schools.
Because if those disadvantaged kids still do well, it challenges your initial belief more strongly.
Exactly. But the paper also recognizes that while that kind of targeted approach might make sense to you if you have those strong beliefs, it might not be as convincing to others who have different beliefs.
That's where the neutrality of randomization comes in.
Right, it's a more level playing field, less open to accusations of bias. But the Bayesian perspective, at least, makes you question whether ignoring everything we think we know and just blindly randomizing is always the best use of resources.
And then there's the whole issue of ethics, right? Especially in situations where there's a strong reason to believe one treatment is better or if there's a chance of harm. Like randomly assigning people to something that might be dangerous when you already have some evidence it's not as good, that can be ethically problematic.
Absolutely. And there are some famous examples of this,
Yeah.
like the ECMO trials. ECMO, it's a treatment for newborns with lung problems. Early observations, not randomized, suggested it was way better than the standard treatment, but then they felt like they had to do an RCT. But some people argued it was unethical to randomly assign babies to the old treatment when it seemed like ECMO was saving lives.
So randomization isn't always the ethical choice, especially if you already have a strong hunch about what's best. And the paper also argues that this obsession with RCTs, this idea that we should always do an RCT even if we have other evidence, can actually hold back scientific progress.
Exactly. By ignoring existing theories and findings from other methods, we're not building on what we already know. It's this idea that RCTs are just these objective theory-free machines for generating truth. And that's just not realistic.
Okay, let's talk about the statistics behind RCTs. We often use regression analysis to get that AE estimate, but there are some statistical traps we need to watch out for, right? What are some of the things that can trip us up?
Yeah, even though calculating the 8E as a simple difference in means or from a regression might seem straightforward, there are all these statistical details you have to be careful about. Like when you calculate the standard error of your 8, you have to account for the fact that the spread of outcomes might be different in the treatment and control groups.
So how much the outcomes vary?
Right. If you don't account for that, you might get the wrong p-values. And that can lead to thinking there's a statistically significant difference when there really isn't, or vice versa.
That's a problem. So what can you do about it?
There are things like using robust standard errors or clustering the errors. But even those methods aren't perfect.
And the paper makes this point that with minimal assumptions, RCTs really only give us solid information about the average treatment effect, not about how different people actually responded to the treatment.
Right. The ATE, it tells you the average, but it doesn't tell you about the whole range of responses. And in the real world, it often matters who benefits the most, who benefits the least, why those differences exist.
So just knowing the average isn't enough.
Right. To get at that variation, you need to make more assumptions or use other sources of information.
What about randomization inference? The paper mentions that even that has limitations.
Randomization inference, it's a non-parametric method. Basically, you're using the randomization itself as the basis for your statistical tests. It's great for testing a very specific hypothesis. Did the treatment have literally zero effect on everyone? But it can't test the more common hypothesis, whether the average treatment effect is zero. And that's often what we care about most.
So it's a tool that's good for certain things, but not others.
Right.
The paper also mentions the Fisher-Barron's problem. I have to admit, that one went over my head a bit. What is that, and why should we care?
So this comes up when you're comparing the means of two groups, like your treatment and control. The standard t-test, it assumes the variances of the outcomes in those groups are equal. But if they're not, the t-statistic doesn't actually follow a t-distribution. And that means your p-values might be wrong.
So you might think there's a difference when there isn't, or the other way around.
Right. And in RCTs, this can be a problem if the treatment itself affects how spread out the outcomes are. Like, it helps some people a lot, hurts others.
And the paper cites this research by someone named Young, showing that statistical significance can be misleading in RCTs, especially when you have other variables in your model.
Yeah, Young looked at tons of published economics RCTs. And what he found was that a lot of those statistically significant results, once you account for all sorts of other things, they weren't so robust anymore. It suggests that some of those findings in the literature might actually be due to these statistical quirks, not a real effect.
So we need to be careful about overinterpreting those p-values. And there's also this issue of skewed treatment effects. When the outcomes aren't spread out symmetrically, the paper gives the example of healthcare expenditure.
Right, because you might have a few people with these huge unexpected healthcare costs, but most people have more normal costs. Or in microfinance, you might have a few wildly successful businesses, but most people have more modest outcomes. And this kind of skewness, it messes up those standard statistical tests that assume things are normally distributed.
They even include some simulations to illustrate this point, right? What did those show?
Yeah, they simulated data with skewed treatment effects. And the results show that those standard t-tests, they can over-reject the null hypothesis, meaning you're more likely to find a significant effect when there really isn't one. And this was especially true when you had smaller sample sizes. They also found that outliers, those really extreme values, could make the distribution of treatment effects bimodal.
So it's not just a smooth curve anymore. It's got two humps, which makes interpreting things even more complicated.
Right.
Okay, so the takeaway here is that just doing an RCT and running a t-test isn't enough. Researchers need to really think about the statistical properties of their data.
Absolutely. Be cautious about strong conclusions from small studies. Consider using non-parametric tests when your data doesn't fit the standard assumptions. And watch out for that Fisher-Barron's problem when you're comparing means.
And beyond all the statistical stuff, the paper reminds us that there are also those more basic threats to validity that can happen after you've randomized.
Yeah, you can randomize perfectly, but things can still go wrong during the study. People drop out, or you don't do a good job of blinding.
Blinding, that's where you keep people in the dark about who's getting the treatment and who's not.
Yeah.
It's incredibly important for minimizing things like the placebo effect.
Yeah, people know they're getting the real treatment. They might report feeling better just because they expect to feel better.
And it's not just the participants. You have to blind the people giving the treatment and even the researchers analyzing the data.
Absolutely. If the people giving the treatment know who's getting what, they might behave differently, and that can influence the outcomes. And even the researchers, if they know who's who, they might interpret the data in a way that favors the treatment.
It can be hard to eliminate all those potential biases. And in some cases, blinding just isn't possible. Like, if you're testing a new teaching method, you can't really blind the teachers.
Yeah, it's much harder in those situations. And sometimes you have to weigh the potential for bias in an RCT against the potential for bias in an observational study. Like maybe in an observational study, you can use administrative data to measure outcomes, and those are inherently blinded because the people collecting the data don't know who got the treatment.
It's a judgment call sometimes.
It is.
So even if an RCT is internally valid, meaning the treatment really caused the outcome in that specific trial, that doesn't automatically mean it's going to apply in the real world. That's the whole idea of external validity.
Right. Internal validity is about whether the cause and effect relationship you found in the trial is actually real. External validity is about whether you can apply those findings to other situations, other people, different environments.
And the paper really cautions against assuming that a trial that's internally valid will also be externally valid.
Exactly.
We're seeing more emphasis these days on including a wider range of people in clinical trials and a move towards these things called pragmatic trials. How do those relate to external validity?
Well, the push for diversity is about making sure the findings from trials apply to more than just a narrow group of people.
So it's about being more representative of the population.
Yeah. And pragmatic trials, they're designed to test how well a treatment works in the real world, not just in this perfect controlled setting.
So it's more about effectiveness in real-world conditions.
Right. And that can help with generalization because it's closer to how things actually play out.
Okay, now the paper goes on to argue that there's more to RCTs than just trying to extrapolate that average treatment effect. What are some other ways that RCTs can be useful?
They make the point that we often get stuck on this idea of, will we see the same 8E somewhere else? But RCTs can tell you a lot more than that. Like, you can get a really detailed understanding of how the intervention works or doesn't work for the specific people in the trial. You can test theories and refine them. And even just showing that an intervention can work, at least under some conditions, can be valuable, even if you don't know how widely it will apply.
It's a proof of concept.
Yeah, exactly.
And they talk about these ideas of simple extrapolation and simple generalization. What do those mean, and why are they often not the best way to use RCT findings?
Simple extrapolation is basically taking the AEE from your trial and just assuming it's going to be the same in a different setting without any real justification. Simple generalization takes it a step further and assumes that 8E is going to hold true almost everywhere.
So you're saying it applies to a much broader population?
Yeah, and the problem with both of these is that they ignore the context. The specific people, the environment, how the intervention is delivered, all of that stuff can change how well a treatment works.
They have this great example, the RAND health experiment, where they estimated the price elasticity of demand for healthcare. What was misleading about how that finding was used?
So they found that medical spending went down by a certain percentage for every percentage increase in copays. And this number, it got used everywhere to inform policy. But later analyses showed that this elasticity estimate, it wasn't nearly as robust or generalizable as people thought. It wasn't some universal constant that you could just apply anywhere.
And they critique the what works literature for sometimes falling into this trap of simple extrapolation, especially those cost-effectiveness analyses that try to compare things across very different contexts.
Yeah, while those analyses can be useful for summarizing findings, they sometimes try to boil things down to these simple metrics like how many extra years of schooling do you get per $100 spent? And they compare those metrics across wildly different places without really justifying why the underlying effects should be the same in all those places.
They make the point that just observing a pattern over and over again without understanding the mechanisms can lead you astray. They use Bertrand Russell's chicken analogy.
Oh yeah, the chicken thinks it's going to get fed every day because that's what's always happened.
But it doesn't understand why the farmer is feeding it. And then, one day, the farmer doesn't bring food, he brings an axe.
It's like that with RCTs too. You might see a consistent pattern in one setting, but if you don't understand why it's happening, you can't be sure it's going to hold up in a different setting.
You need to understand the underlying mechanisms. And they bring up this concept of support factors and explain how the AE depends on how those factors are distributed in the study population. What exactly are support factors?
Support factors are basically the conditions that have to be in place for a cause to have its effect. Like flipping a light switch won't turn on the light unless you have electricity, a working bulb, and the wiring's all connected.
So it's not just the cause itself, it's the whole context.
Right. And the AE you get in an RCT, it depends on how common those support factors are in the people who are in the trial. So if those support factors are different in another population, you can't expect the AE to be the same. And those support factors, they're often things like social norms, economic conditions, cultural stuff, all things that can vary a lot from one place to another.
And even the way you measure the outcome can affect how generalizable the results are. Right?
Oh, yeah. Even if the underlying effect is the same, if you measure it differently in different studies, you're going to get different results. Like, imagine a program to improve literacy. If one study measures it with a standardized test and another uses teacher ratings, they might find different effects, even if the underlying impact on literacy is the same.
It's all about measurement. So this really highlights the importance of understanding the underlying mechanisms, not just the biological or psychological stuff, but also the social, cultural, economic, political context.
Exactly. Mechanisms are what drive those cause and effect relationships. If you understand the mechanisms, you can explain why something works or doesn't in a particular context. And you can make better predictions about how it might work in a different context.
But even without all that, there are some limited cases where RCTs can give us valuable information without having to extrapolate.
Yeah, they're great for disproving very general theories. Like if a theory says something can never happen and then an RCT shows that it can, at least under some conditions, that's important. They're also good for confirming specific predictions from a theory.
So testing very specific hypotheses.
Right. And they can be useful for just showing that an intervention is capable of working, even if you don't know yet how broadly it will apply. It's like a proof of concept.
And in public health, if you're dealing with a well-defined population and your trial participants are a random sample from that population, then the AEE you get from the trial can be a good estimate of the effect for the whole population.
Yeah, that's often the goal in public health, to improve the health of a specific population.
Right.
But even then, you have to be careful about things like contagion effects. Like, what if the people in the trial start behaving differently because of the intervention, and that influences the people who weren't in the trial?
It gets complicated quickly. Now, the paper talks about some ways researchers try to make RCT findings more applicable to new settings. Things like reweighting the data and looking at results within subgroups.
Right. Reweighting is basically adjusting the results statistically to account for differences between the people in your trial and the people you're trying to generalize to. And stratification is looking at the effects separately for different groups within your trial, like age groups, gender, income levels.
So you're trying to see if the treatment works differently for different types of people.
Exactly. But these methods, they often require information that you don't get from the RCT itself. You need to know about the characteristics of that new population, how those characteristics might interact with the treatment.
And this takes us back to the point that you can't just assume the AEE is going to be the same everywhere.
Right. To make any general claims, you need to go beyond simple extrapolation. You need to be explicit about the causal structure you're working with. And that often means more modeling, more assumptions than some RCT proponents might be comfortable with. But it's necessary.
And to use those methods for adapting results, you often need data from observational studies, things like social structures, economic conditions, stuff like that.
Yeah, you need that broader context. RCTs don't happen in a vacuum. To generalize responsibly, you need to bring in information from other sources, other studies, existing theories.
So it's really an integrated approach. And the paper challenges this idea that RCTs are always the best, that they trump all other evidence. They argue that we need to be more nuanced, look at the whole picture.
Absolutely. And when RCTs and observational studies disagree, we shouldn't just dismiss the observational studies. We should try to figure out why they're different. Those differences can tell us a lot.
It's about investigating those inconsistencies, not just assuming one method is always right.
Right.
Okay, now the paper also explores this idea of using RCTs not just to estimate average effects, but to actually build and test theories.
Yeah, and this is a really powerful way to use them. When you have a theory and you design an RCT to test a specific prediction of that theory, you can really advance scientific understanding. There's a great example of the study on graduation programs. These are programs aimed at helping people escape poverty. They did RCTs in multiple countries and found that these programs can be effective. It wasn't just about the average effect. It was about testing this idea that these kinds of multifaceted interventions can break the cycle of poverty.
So the RCT was embedded in this larger theoretical framework.
Exactly. And economists have been doing this for a long time, combining theory and experiments. Think about those early income tax experiments. By using theory to guide their RCTs, they were able to learn not just about the immediate effects, but also about the potential long-term consequences. In Kenneth Arrow's work analyzing the Rand Health experiment data, that's a great example, he used economic theory to try to predict long-run changes in healthcare demand based on those short-term results.
So theory helps you make sense of the findings and make predictions beyond the trial itself.
Right. And even simple economic principles like thinking about how policies affect prices and incomes can be really useful for understanding and extending RCT results. But of course, we have to acknowledge that people aren't always perfectly rational. Behavioral economics has taught us that.
People don't always act in their own best interest.
Exactly.
Yeah.
But even with those complexities, having some kind of theoretical framework is essential. And theory can help us with practical problems too, like what do you do when people in your RCT don't actually follow the treatment plan? Theory can help you figure out how to analyze the data in those situations.
Okay, the paper then tackles this issue of scaling up. Why might something that works well in a small RCT fail when you try to implement it on a larger scale?
Yeah, this is a really important question. When you scale up, you can get all sorts of unintended consequences, things that weren't captured in that initial small trial. And it often comes down to what economists call general equilibrium effects, or violations of something called the Stable Unit Treatment Value Assumption, or SUTVA.
SUTVA, that sounds complicated.
The basic idea is that it assumes what happens to one person in the trial doesn't affect what happens to other people. But when you scale things up, that's often not true.
The paper uses the example of a fertilizer.
Right. Imagine a fertilizer that seems to boost crop yields in a small trial. But what happens if everyone starts using it? Well, if the overall supply of that crop goes up a lot and the demand doesn't change much, the price is going to drop. So even though farmers might still be producing more, they could end up making less money because the price is lower.
So something that seemed beneficial at a small scale could backfire when you scale it up, and they point out that this can happen in other areas too.
Absolutely. Things like education programs or cash transfer programs, if they're successful, they might change the demand for certain goods or services, and that can affect prices.
So you can't just assume that what works for a small group will work the same way for a large group.
Right. Host.